In this paper, we present a method for mapping distributed radiation fields in 3 dimensions. The distributed radiation mapping algorithm operates over a discretized grid in 3 phases: estimation, propagation, and curiosity. In the estimation phase, linear regression is applied to the readings from a neighborhood of each cell to derive an estimated gradient and mean. A confidence metric for the gradient is derived using Shannon entropy, while a confidence metric for the mean corresponds to the number of readings found in the neighborhood. Mean and gradient propagation takes place over a specific order. Both orders are derived by first finding cells who have valid estimates for the gradient and mean, and then recursively finding their neighbors, assigning incrementing cell levels to each layer of neighbors. Gradients are propagated using neighbors who have a lower propagation level, by taking the average of their gradients weighted by their gradient confidences. Means are propagated by a similar method, calculating the neighbor's contribution to the cell of interest and averaging the contributions weighted by their neighbor's mean confidences. Finally, in the curiosity phase, a curiosity waypoint is derived by finding the point within the platform's safe navigation bounds, which maximizes a metric that depends on the propagated gradient entropy and the propagated mean. This waypoint guides the platform to areas for which little data has been gathered and has a large expected mean intensity. The path to the curiosity waypoint is supplemented by intermediate waypoints, which are displaced from the original vector to provide greater variance in the measurement positions. To validate the performance of the radiation mapping algorithm, 2 experiments are presented with real gamma radiation sources using a platform called the Resilient Microflyer Gamma, or RMF Gamma. RMF Gamma is a collision-tolerant robot with onboard visual inertial odometry and is equipped with a scintillator and custom pulse-counting circuitry. In the first experiment, the robot follows the curiosity path, quickly locating both distributed sources. In the second experiment, the robot is commanded to follow a fixed grid pattern. In both experiments, the robot successfully maps the distributed radiation fields.